All right, Matt, we're going to go through your electricity notes here, and you're going to try to pay attention, try to take some notes down. I want you to highlight some things as we go through this PowerPoint. Key word for static electricity, to define it, is it's non-moving charge. So it doesn't flow, it just snaps. Like when you get when you get a shock on a doorknob, that's static electricity. It's a jump of charge, jump of electrons, but doesn't flow. So it's non-moving charge, just jumps and it's done. So there's three ways you can get a shock. You know this: friction, when you're scraping your feet across the carpet, that builds up electrons and causes a flow of electron from one object to another, friction. Rubbing your head under a blanket, rubbing a balloon on your head, those are examples of friction for charging up your hair. Your hair stands on end because it's got electrons built up on the surface, and those electrons are all negatively charged, so your hair repels itself because of the electrons building up. When you transfer the electrons from the balloon to your hair gets charged up. Conduction is when you simply touch an object that is charged. A good example of conduction is when you have a doorknob and a metal doorknob, and you're all charged up with scraping your socks across the carpet, and then you touch that doorknob. As you touch it, it jumps from you to the doorknob. You get a shock. Induction, sometimes if you have a lot of static electricity buildup, a lot of electrons built up from scraping across the carpet, which would be friction, and then you come close to an object, it causes induction. It causes those electrons to transfer, not by touch, not by rubbing them together, but they actually jump across the space between the two objects. That's called induction. For example, if you're standing outside and a cloud overhead comes that is charged with static electricity during a lightning storm, you know you've been charged by induction when your hair stands on end. People, just before they get struck by electricity, their hair stands on end when they're standing there in a field, and that's because they've been charged by the clouds overhead via induction. So think of induction as not touching, but you're still getting charged as that charged object moves near you. Okay, so here's some examples just described there. We just talked about that. An insulator, think of when you insulate something, you don't want anything to penetrate it. So an insulator is something like a cord that has rubber on the outside of it. That rubber is an insulator. We know rubber is a good insulator. We know wood is a good insulator. Electrons or electricity can't pass through it. So we always insulate our cords with plastic or rubber, or we use wood to prevent you from getting an electric shock. A conductor is something that electrons can pass through. We know our bodies can conduct electricity because if you touch an electric fence, electrons will flow from that fence through you, and you're charged and you can be electrocuted. Same thing with metal. We know metals are good conductors of electricity. We know water is a good conductor of electricity. You don't want to drop your hair dryer in the bathtub because water will conduct that electricity from the dryer to your body through the water. So when we talk about electric fields, we're talking about the force that is emitted by that electrical object around it. So here's two types of electrical fields. So this just means that there's a force of electricity that goes out from one source in multiple directions. So we call it a monopole because the source of the charge is in one location. A dipole is two sources of charge, or a flow of charge going from the positive to the negative. So it's called a dipole. So here we can see there's one source of electric charge flow. Here there's two sources. So we call that a dipole. So the two types of electricity, there's static electricity that we said doesn't flow, and lightning is an example. Shocks, on your finger when you touch a doorknob, rubbing your hair on a balloon, that's all static electricity. Doesn't flow. It just charges, it snaps and it's done. Current electricity is flowing through a circuit. So that's when you plug something in, things always flow. We can see here that it says that the negative is high energy and positive is low energy. Let's see what that means. Direction of positive flow. I don't know what that means. Anyway, the only thing that flows through a circuit are electrons. So electrons flow from the negative end to the positive end. So every battery, you'll notice, has a positive sign and a negative, or a negative sign and a positive sign on it. So you got to make sure you put it in your device the right way so the electrons flow out of the negative terminal through your device. Let's say this is a light bulb, and then back through the wire to the positive side. So negative to positive is the way electrons flow. They build up on the negative terminal, they flow through to the positive terminal, and as electrons pass through a device, they get clogged up in there, and if it's a light bulb, it causes that light bulb to glow. There's a little filament in there that glows as the electrons get clogged up inside that bulb. So current electricity is flowing electrons. Static electricity is just a discharge of electricity that stops. It doesn't continue to flow. So when we look at voltage, you've heard of a 9-volt battery, 12-volt battery. There's different voltages, and that just means you're looking at the difference between the energy at one side of the battery to the energy at the other side of the battery. The more push behind the electrons, the higher the voltage. So just think of voltage as the push behind electrons as they're flowing through a circuit. Higher voltage means higher push. Okay, so that's what we're talking about here, voltage, the push behind electrons. So the faster they're flowing through, the more powerfully they're flowing through that wire, the more push. Okay, so that's measured in joules, volts is voltage. That's easy to remember it, measured in volts. And then resistance is what opposes voltage, so it's the push back. So you have voltage pushing in one direction and you have resistance in the other direction. So some wires are more resistant, so as a result they glow. Like a toaster, when you pop your toast down, the little wires inside the toaster glow because those wires in the toaster have a high resistance. There's electrons flowing through them with the help of the push, the voltage, but the resistance in the wire causes electrons to slow down in the wire, and then they glow as a result of being pushed through that wire that doesn't allow good flow. It has a high resistance. So then we look at current. Current, think of that as the speed through which it goes through. So voltage is the push behind the electrons, so how much power they have behind them. Resistance is like friction in the wire, you know, how fast they can get through there in terms of the push back. The greater the friction in the wire, the more resistance. And then current is the speed of how fast it goes through the wire. So it's measured in coulombs per second. And coulomb is just a measure of electrons, amount of electrons. So a number of electrons per second makes sense that are passing through a spot in a wire, that's current. So Ohm's law relates those three terms together. It says that the current, that means how fast electrons are running through a wire, depends the push behind the electrons divided by the push back against the electrons, which is the resistance. So it's I equals V divided by R. So you got to know your units to know if you're being given voltage, resistance, or current. Voltage, the units are volts, so that's easy. You know where that goes. Resistance, the units are ohms. It has this horseshoe-shaped unit. That's the symbol for ohms. Okay, so ohms is resistance. It's the push back. It's the resistance to flow. It's the glowing of a bulb. The more a light bulb glows, the more resistance in that little filament inside of the light bulb. And you know when that filament breaks, the light bulb doesn't work anymore, because you can shake a light bulb and hear that filament rattling around in there. That's because that wire in the light bulb that has a high resistance is broken, and electrons can't flow through it anymore, and it's not going to glow. So if you're given the voltage, you're given the resistance, you want to know the current. So you just take current equals the voltage, which is 120, divided by the resistance, which is 20. 120 divided by 20 is 6. And the units for current is amps, or amperes. And amperes is another way of saying coulombs per second. So it's just, again, it's a measurement of speed, how fast it's going through the wire. Okay, another term you have to know is power, which means if I have these, let's say you put a battery in and the current's flowing through the wire, and I have a certain voltage battery, and the wire has a certain amount of resistance, how much energy how fast is the energy coming from that battery being sucked up. So that's what power is. It's the rate at which energy is consumed or produced. So the formula for power is in watts. So a 50-watt bulb is telling us that I have, let me think about that. Oh, it says right here. Okay, so considering the voltage, they give you the power is 100 amps. Remember what amps is? That's a measure of current. So current is the letter I. So if you're trying to figure out voltage, you just take this formula and manipulate it. So power is 100. Voltage, you don't know what it is. It's asking you what the voltage is. And then the current is 0.833. That's how fast it's going through. So it tells us how fast are the electrons going through. It tells us how fast energy is being consumed. You got to find out what is the push of those electrons going through the wire. Using this formula, it's simple algebra, you can calculate that voltage. So you just take the 100 watts, which is the voltage, divided by the current to find the, this is the power divided by the current to get the voltage. So we'll stop at this point, and I'm going to give you some problems to work with power, current, voltage, and resistance, and you can check your answers, and we'll come back.